Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 1 of the Linear Tidbits series. A linear relation is the most basic type of relationship that can exist between two variables. Literally, linear refers to any straight line relationship, a direct relationship which is free of bends and curves. Even though the most basic, it is one of the most important concepts you will be encountering time and time again throughout your math career. Try to get a good handle on these concepts early on, and they will serve you well as you proceed into higher level math. In this video series, we will find out exactly what it means for two variables x and y to be linearly related, and what fundamental characteristics can be derived from such a relationship. Here are some tidbits directly from Websters Dictionary. And here's Webster's Dictionary in front of us. I went to the search bar, I typed in the word linear, and here's the output. It says of, relating to, resembling, or having a graph that is a line, and especially a straight line. Straight, involving a single dimension, that is one-dimensional, of the first degree with respect to one or more variables. In other words, only x to the power 1, or y to the power 1, or z to the power 1, etc. can appear. Of relating to, based on, or being linear equations, linear differential equations, linear functions, linear transformations, or linear algebra, characterized by an emphasis on line, and it goes on and on. Let's have a look at the panel on the left. And it says over here linear accelerator, which is a concept in physics. Linear algebra, definitely a concept in mathematics. Linear combination, math. Linear dependence, math. Linear equation, math. Linear function, math. Linear independence, math. Linear interpolation, math. Linear measure, math. And let's see what else there is. Linear motor, concept in physics. Linear perspective, concept in drawing or architecture. Linear programming, math. Linear regression, math. Linear space, math. And finally, linear transformation, math. So you see that linear is very mathematical in nature. The word linear is all about math, and it comes up in math very, very frequently. And you're going to carry on using the word linear for quite a number of years to come if you pursue mathematics in any sort of depth whatsoever. Okay, so we're going to shut down Webster here, and we're going to start our lecture on linear tidbits. We're going to proceed to slide 1. And this is the only slide we will be discussing for this video because there's a lot of information appearing on this slide. The title says characteristics of a straight line. So there are a number of concepts over here that need to be presented, but what I need for you to do is use your imagination, pretend like white out everything in blue, white out everything in red, pretend there's nothing on this page except for maybe the title and the grid underneath, the grid in the background. Okay, no axes, nothing, just the grid. You'll notice the grid consists of parallel horizontal lines, much like the lines you would encounter in a city going from west to east. Also, there are vertical lines. They're vertical parallel lines, very much like the north-south lines of roads in a city. So now I come from the city of Toronto, so I'm going to think about this grid as the grid for the city of Toronto. And I'm going to go to the center of the city over here, somewhere in the center, and put a dot there. And I'm going to declare that dot to be the origin. From the origin, I will make all measurements. So all measurements will be made relative to the origin. So you can think about the origin as City Hall for the city of Toronto. Okay, so the next thing I want to do after I choose my origin is to bring in a horizontal line. I'm going to bring it up to the origin right there. There's the origin right there. I'm going to take a pencil and draw a horizontal line. And then I'm going to back off of that line, and I would like to graduate the line. I would typically put a 1 there, 2 there, 3, 4, 5, etc. And on the left-hand side, I would typically put -1, -2, -3, -4, etc. So this is the positive x-axis. That's the negative x-axis. We have negative numbers along here and positive numbers along here. And you'll notice as we proceed from negatives towards positives, the x values are increasing. So the x values increase from left to right. And that's why we put the x label on the right-hand side of the x-axis. Okay? So this is called the x-axis. You put numbers along the bottom over here. These are called graduations. And then essentially we're done with the x-axis. Put the label down. Don't forget to put the label down. The label is always in the direction of increasing x values. The next thing I want to do is remove the horizontal line and bring in a vertical ruler and let it pass right through the origin. And then I would take a pencil and draw a vertical line. And then we'll back off that line. The next thing you would like to do is graduate the y-axis. We're going to call the vertical axis the y-axis. So typically I would put a 1, 2, 3, 4, etc. And then on the bottom I would put -1, -2, -3, -4, etc. So proceeding towards the bottom over here, we have negative y values. Proceeding towards the top, we have positive y values. The direction of increasing y values is bottom up. Okay, so bottom up. And that's why we put the label y on top. Because y is this direction over here from bottom up is the direction of increasing y values. So that would be the appropriate convention for placing an x-axis down and a y-axis down and labeling the x and y axes. I'm going to move this ruler out of the way. And you'll notice that the positive x-axis actually points east, the negative x-axis points west, the positive y-axis points north, and the negative y-axis points south. Okay, alternatively, we can say the positive x-axis points to the right, the negative x-axis points to the left, positive y-axis points up, the negative y-axis points down. Okay, and now we're in a position to try to locate points in our city. We set up the grid, we set up the axes. It's time to learn how to locate points in the city. Now, suppose P1 over here stands for my house, and P2 stands for your house. So my house, P1, will have coordinates. It'll have an address. Your house, P2, will have its own address or coordinates. Now let's see how we might get to each house. Suppose one unit in the x direction corresponds to, or one block in the x direction corresponds to 1 unit. And 1 block in the y direction also corresponds to 1 unit. So we have a 1-to-1 scale here. Now, more about scaling, just a pause. If this is 1 unit in the y direction and this is 1 unit in the x direction, we call this a 1-to-1 scaling. If 1 block, let's say, represents 2 units, so this would be 2, 4, 6, this would be 2, 4, 6, it's still a 1-to-1 scaling. Okay, because the same block will represent 2 units in the y direction and 2 units in the x direction, so it's still a 1-to-1 scaling. But I could also have a differential scale set up. I could have 1, 2, 3 along the x-axis and 2, 4, 6, for example, along the y-axis. We have a differential scale. Okay, alternatively, I can make this 2, 4, 6 along the x-axis and 1, 2, 3 along the y-axis. Again, a differential scale. The type of scaling you use depends on very much on what sort of graph you're going to plot. Okay, so let's get back to locating our homes over here. Let's say I'd like to locate my house that's located at P1, this dot right here. How might I get there? Well, there's a few ways to do it. I'm going to discuss 3 ways to do it. We can go left 7 units and down 3 units. That's one way to do it. We can go west 7 units and south 3 units. That's another way to do it. Or we can use numbers. We can say -7 minus 3. -7 minus 3. Which is the easiest? Of course, the coordinates. Okay, -7 minus 3 is easier than saying left 7, down 3. Or west 7, south 3. Much easier to say -7, -3, and we know exactly where my house is located. Now let's try to locate your house. We could say right 4, 6 up. We could say east 4, 6 north. Or we could say +4, comma, +6. +4, comma, +6 using coordinates. So inside over here, these would be the coordinates. We would have +4, +6 as the coordinates of the point P2. Likewise, for the point P1, we would write down -7, comma, -3. -7, comma, -3. So now we know how to locate points in the XY plane. By the way, the XY plane is also called the Cartesian plane, named after the great mathematician René Descartes. Just to recap, you'll recall that we set up a grid in the background. We chose an origin, and we drew a horizontal axis through the origin. We called it the x-axis. We drew a vertical line through the origin, and we called it the y-axis. We graduated the x-axis. We graduated the y-axis. And at that point, we were in a position to locate points anywhere in the Cartesian grid or the Cartesian system. And we learned how to locate P1. We learned how to locate P2. P1 is located by going left x1 units, going down y1 units. P2 is located by going to the right x2 units and up y2 units. Okay, so now we know how to locate points anywhere in the xy plane. The next order of business is that recall that this is my house, this is your house. What I'd like to do is drive from your house, drive from my house to your house. And I could drive along a winding road. I could go along this path, which is usually what happens in a city. It's very unusual to find a winding road that goes directly from my house to your house. Or I could drive along a straight line. Okay, a straight line segment P1 to P2, that is to say along the red. Okay, those are the three choices. If I choose to go along a winding path, then we say the relationship between x and y is nonlinear. If I choose to go along the direct path from P1 to P2 along the red line, then we say that the relationship is linear. And I could also choose to go along a straight line path as well, but it's composed of two segments, a horizontal segment and a vertical segment. Okay, that's also linear and linear. But again, the winding road would denote a nonlinear relation, but the straight line path denotes a linear relation between x and y. The next thing I would like to do is to bring in a couple of vertical rulers, one through the point P1 and one through the point P2, like so. And there's P1, that's my house, that's P2, that's your house. And we're looking at the path going directly from the left ruler to the right ruler in the horizontal direction. Okay, the run is defined to be the difference in x values. So this would be x2, that would be x1. It's defined to be x2 minus x1. We use the symbol delta x as a short form for x2 minus x1. Delta is a Greek letter implying difference, and x, of course, is the difference in x values. And literally, we call that the run. So the run is defined to be the difference in x values, which is x2 minus x1. For example, x2 over here is 4, x1 over here is minus 7. So x2 minus x1 would be 4 minus minus 7, which is 11. And that's what constitutes the run. Another concept is the concept of the midpoint. Let's say we want to establish the midpoint between the left ruler and the right ruler. It's somewhere along here. Let's say the left ruler represents one of your marks, and the right ruler represents another one of your marks, let's say on two different tests. How would you obtain the average of those two marks? Wouldn't you add the marks and divide by 2? And that's exactly what we do over here. X1 is my mark on the second test. Sorry, x1 is my mark on the first test. X2 is my mark on the second test. To get the average mark, I would do x1 plus x2 divided by 2. And let's see if that works out. X1 is negative 7, x2 is 4, so x1 plus x2 would be negative 7 plus 4, which is negative 3, and then you divide by 2 to get negative 1.5. And there's x equals 0 there, negative 1, negative 1.5, and lo and behold, that looks like the midpoint. So again, to recap, to get the midpoint of this horizontal line segment, you add the x values together and you divide by 2. So you have x1 plus x2 divided by 2 will give us the midpoint. And now we remove the vertical rulers in favor of horizontal rulers. I'm going to let the first ruler over here go through my house, P1, and I'm going to let the other horizontal ruler go through your house, P2. This time we're going to focus our attention on the blue line segment between the rulers. The rise is defined to be y2 minus y1. y2 over here is 6, y1 is negative 3, so y2 minus y1 is 6 minus minus 3, which is 9. Okay, so the rise is effectively this distance. Rise, y2 minus y1, We use delta y as a short form for y2 minus y1. Again, delta means difference, and delta y means difference in y values. Okay, so it's y2 minus y1. Y2 over here is 6. Y1 is negative 3. So 6 minus 3 is 9. And that will give us the rise. Now let's talk about the midpoint. Again, your marks this time would be y1 for test 1 and y2 for test 2. And to get your average mark, you would do y1 plus y2 divided by 2. That's how you get an average of any two y values or any two marks. y1 plus y2 divided by 2. And let's see if this works out. y1 is negative 3. y2 is 6. So negative 3 plus 6 will give you 3. And then 3 divided by 2 is 1.5. Let's try it. We'll start off over here. This is y equals 0, y equals 1, y equals 1.5. Looks good. That looks like the midpoint of this vertical line segment. Okay, so to recap, how do we find vertical midpoint? We just add the y values together and divide by 2. So we have y1 plus y2 all over 2. And that'll give us the midpoint. Now we're going to remove both rulers and recap. The run over here is the horizontal distance from P1 to P2. We use delta x to indicate the run, and it's x2 minus x1. The rise is the vertical distance from P1 to P2. There it is right there. We call it delta y, and it's y2 minus y1. The midpoint of the horizontal line segment here is x1 plus x2 divided by 2. And the midpoint of this vertical segment here is y1 plus y2 divided by 2. Now altogether that says that the actual midpoint M, which is the halfway point from P1 to P2, if I were driving along this straight line path from P1 to P2, it would be the halfway point. The x value should be given by x1 plus x2 divided by 2, and the y value of this point should be given by y1 plus y2 divided by 2. Let's check it out. x1 plus x2 divided by 2, you'll recall, was negative 1.5. There we are. And y1 plus y2 divided by 2, you'll recall, was 1.5. So we go negative 1.5 and then positive 1.5, and lo and behold, we're at the midpoint. So the midpoint formulas actually work out well. Okay, the next order of business is to discuss the ratio of rise to run. The rise divided by the run is called the slope of the line. So we can either write rise over run as the slope, delta y over delta x is the slope, or y2 minus y1 all over x2 minus x1 as the slope. So the slope is always a ratio of delta y over the delta x, the difference in y values over the difference in x values. So for example, if we go over 1 unit in x, how many units in y do we go up? That's called the slope. If we go over 1 unit in x, how many units in y do we go up? Again, that's called the slope. If we go 1 unit across, how many units in y do we go up? Again, the slope. If we can start anywhere along the line segment P1, P2, by the way, that's what it's called, the line segment. P1 is the left terminal point, P2 is the right terminal point, and again, M is the midpoint. By the way, if we extend the line segment P1, P2 to infinity upwards and to infinity downwards, the totality of all that is in red is called a line. So a line consists of an infinite number of points extending to infinity up here and infinity down there. So when you extend a line segment forever in either direction, it is called a line. Okay, a line segment itself must have a left terminal point and must have a right terminal point in order to be a line segment. Okay, let's get back to the slope, which is rise over run. You'll notice if you go 1 unit across, look how many units you go up. That's a slope. 1 unit across, how many units up? That's a slope. 1 unit across, how many units up? No matter where we start going 1 unit across, we go the same number of units up. 1 unit across, same number up. 1 unit across, same number up. 1 unit across, same number up, etc., etc., etc. This graph looks like it might have a slope of 1. Okay, roughly 1 unit across, 1 unit up. 1 unit across, 1 unit up. Therefore, it has a slope of 1. Nearly, anyway. Okay, so we've discussed about slope. And slope is also referred to as rate of change. And we notice that for a line, the slope is the same. No matter where you start along the line, the slope is the same. Because 1 unit across will generate the same number of units up. 1 unit across, same number of units up. 1 unit across, same number of units up. No matter where we are along the line segment. So that we say that along a line segment, the slope is constant. Okay, and that's that's the key property of a straight line, is that its slope is always constant, no matter where you are along the line. Here, the next order of business is to talk about distance. So suppose, again, this is my house, and suppose this is your house, and I'm driving along a straight line path from my house to your house. Suppose I'd like to know what distance I travel going along a direct line path from my house to your house. Okay, you'll notice that the run, the rise, and this line segment, P1, P2, forms a right angle triangle. And you know that whenever we have a right angle triangle on our hands, we can always use the Pythagorean theorem. Okay, the run and the rise are the legs of this right angle triangle. And the segment P1, P2 is the hypotenuse of the right angle triangle. There's the 90-degree angle right there. So we have hypotenuse here. The run is one leg and the rise is the other leg. If you'll recall, the Pythagorean theorem says that d squared, which is the distance between P1 and P2, d squared is equal to run squared plus rise squared. Or d squared equals delta x squared plus delta y squared. The points where this line cuts the axes, here and here, are special points. This point is called the x-intercept, and it's where the y value is equal to 0. This point is called the y-intercept, and that's where the x value is equal to 0. So these are essentially opposite each other. This is where the y value is 0, and that's where the x value is 0. So the coordinates of this point would be x int, comma 0. The coordinates of this point would be 0, comma y int. So finally, we turn our attention to this equation up here. Notice that we do have an equal sign, so it really is an equation. On the left, we see y, but it appears to the power 1. On the right, we see x, and it appears to the power 1 as well. That's why we call this a linear equation, because both x and y appear to the power 1. This linear equation contains two parameters, m and b. These are called parameters. And as you change the parameters, the characteristics of the line will change. M specifically is that slope that we were talking about earlier. It's defined to be delta y over delta x. And the b is the y-intercept. It's where the line crosses the y-axis. So again, m is delta y over delta x, the slope, and b is the y-intercept, where the line cuts the y-axis. And we'll talk this over here is only one form of the equation for a straight line. It involves the slope and the y-intercept, therefore it's called slope-intercept form. There are other different forms that do the same job, but we won't discuss them here. We'll discuss them in a later video. So let's have like a brief recap of all that we've done. Okay, we set up an x-axis, we graduated the x-axis. We set up a y-axis, we graduated the y-axis. We put the label on the x-axis in the direction of increasing x. We put a label on the y-axis in the direction of increasing y. Next, we chose 2 points. That was my house. This is your house. The point P1 has coordinates x1, y1. The point P2 has coordinates x2, y2. The x, y, y1 are like the address of my house so that I can establish its location. x2, y2 is the address of your house, so we can establish your house's location. If we draw a straight line between P1 and P2, that's called the line segment. We've talked about the midpoint M as the average of the x values and the average of the y values. We've also talked about the run, which is denoted by delta x, which is x2 minus x1. We talked about the rise, which is denoted by delta y, which is y2 minus y1. And we've also said that the ratio of rise to run, that is delta y over delta x, which is y2 minus y1 over x2 minus x1, is called the slope. And it corresponds to m in the equation of the line. We also said that this is called the x-intercept. It's where the line crosses the x-axis. And we mentioned that this is the y-intercept where the line crosses the y-axis. And the y-intercept is the same as the b value in the equation of the line. And the slope, which is delta y over delta x, is the same as the m value in the equation for the line. And we also discussed about distance, the distance between 2 points. The distance squared is just the run squared plus the rise squared. That comes from the Pythagorean theorem. And the equation of the line is a complete mathematical description of every point on that line. So this actually describes the relationship between x and y, and we call it a linear relationship. And that's over and out for this video. Thank you very much. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MATLAB Tutorials in Toronto.